Okay, welcome back. This is Chapter 12. Now, Chapter 12 is a bit geeky, so just kind of bear with me for a minute. So the title of this thing is The Stack, the Heap, and the Garbage Collector. That kind of sort of sounds like a movie, doesn't it? So there's some terms you're going to have to learn, so let's just go through them. One is, what the heck is the stack? And then the heap. And then this term inflation, which we've used before, so that one should not be new. Okay, so the way it works is if I create a variable like edit text, ET display, okay? Or if I just go in here and just create me a regular honest to God variable, like, I don't know, we'll go in here and we'll say int age is equal to 12. Okay. Memory in a modern system is composed of two chunks. Well, actually, there's more than that, but bear with me. The stack is where these variables are stored, okay? So the ET display variable and the age variable are stored on the stack, okay? And as you add more variables, they stack up. Boop, 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 boop. And as the variables disappear out of scope, the stack compresses. So the stack is always just growing and shrinking, growing and shrinking as things either come into scope, it grows, and goes out of scope and they go back down. Okay. That part is pretty straightforward. So if you recall that the reference type and a primitive type, you remember all that good stuff? Okay, good. So a primitive type, like on line 18, is age. Well, it just so happens that primitive types are small enough so not only does the variable get stored on the stack, but what it points to is stored there as well. Now, I'm probably not explaining in a perfect way, but age is stored on the stack, and the stack is big enough so that it can hold the 12 on the stack. Okay, it's not like a separate location. But ET display is not a primitive type. It's a reference type. So ET display is stored on the stack, but the contents can't fit there. The stack is designed to be, short and sweet and fast moving kind of a thing. So it doesn't know how big things are. Okay, now that's the key. Primitive types, I always know how big it is. I know how big an integer is. I know how big a long is. I know how big a double is. I don't have to go look. I know exactly how big those things are. So I can, when you say, I want to create a double, the machine's going to say, great, that's 8 bytes. I know exactly it's going to be 8 bytes. I'm going to put 8 bytes on the stack. Perfect. But if you said, I want to put a string for this guy's first name on the stack, the machine's going to go, well, I have no idea how big that's going to be. I mean, it could be Bob, or it could be Ebenezer. Right? You don't know. So that's why reference types are stored in two different locations. The variable is still stored on the stack because all variables are stored on the stack. And yet the thing, like first name, is stored on another chunk of memory called the heap. All right. So the stack and the heap. So all UI elements, buttons and edit texts and all those things, those are classes, right? And so when you instantiate a class, that's a reference type. Okay. So the stack is usually very neatly organized, just by its very nature. The things being stored there are very, very small. I think the largest thing that can get stored there is, I don't remember now. Somewhere around in the vicinity of about 8 bytes. That's about it. And so it doesn't require any maintenance. When things come into scope, it gets grown up. So let's build us a method here. Okay? So I'm going to do public void sum method. And I'm going to build me a couple variables. I'm going to say int, I'm going to do age again a second time. Hey, is that going to cause a problem? It's probably not a good idea, but no, we'll not call a problem. And then I'm going to say string first name is equal to Bob. And then just for the heck of it, let's spit those things out. So ET display append age equals age. Whoa, I didn't mean to hit the carriage return. And first name equals first name plus a carriage return. Okay. So right now, if we were to kind of look at this thing, and I'm going to call this thing called sum method. Okay. I'm going to change this because I just don't like the idea of having two variables. I mean, they're in different scopes, so there's not really a conflict. I just don't like doing it because it looks like it's a conflict. So I'm going to change this one to kumquat. Okay, cool. Now, as the machine is moving along, it's going to say, well, I need to create 8 bytes for this to store the variable ET display. I need 4 bytes to store this thing called kumquat. Now I need to call the heap to allocate however big this thing is, because I don't really know how big it is. And then when you get to sum method, then it's going to go down here and say, wait a minute, I need another 4 bytes, and I need another 4 bytes, plus I need, that's probably 7 or 8, probably 8 bytes, counting a 0 here. So the stack would start off having this item in it, this item, and then later it would add 2 more. Boink. And then when this thing finishes, when this curly brace gets hit on line 29, these 2 guys go away. So the stack starts off, it's got 1 item, 2 item, 3 item, 4 item, boop, back down to 2. See how this thing works? So, because when things go out of scope, they drop off the stack is basically self-maintaining. I don't need anything to make it smart, smarter than it is. I mean, it just maintains itself. There's no need. The stack grows, the stack drops. No big deal. The heap, on the other hand, when it gets called, it is possible that you could create like string for first name and then a whole bunch of other stuff. Now, so far so good. It's gonna create a chunk of memory in the heap. And then when that one goes out of scope and you turn around and ask for one that's bigger than that, it won't fit in the hole where that one used to be. Is that making sense? In other words, here's a chunk of memory. Here's a spot that holds 8 bytes for first name Bob, okay? But the second time through, it's going to be Ebenezer. Well, it won't fit. So it's going to leave that a hole in memory and scoot over and find another spot to create the second name. Okay? Is that making sense? So the heap, after a while, it could look like Swiss cheese. It could have all sorts of holes in it. And so it does require some sort of maintenance. And the maintenance is called garbage collection. Okay. So garbage collection occurs, and what the machine says, hey, hang on, let me just put your application on pause for just a second, and let me go coalesce all these holes and rearrange things so that all of the free memory is all blocked together, and all the used memory is all blocked together, and coalesce all the holes so that when I ask for memory, I don't have to go look for it. Oh, well, it won't fit here. Wait, oh, but it won't fit here. Oh, but it won't fit here. Oh, here's a spot. That takes time and energy. Okay, so garbage collection is not normally something that you, the programmer, would invoke. The machine will just look at itself and say, look, I got plenty of memory. I don't care if I've got a bunch of holes in memory. I don't care. Until you keep on going and keep on going, and it's sort of like watching the gas gauge on your car. You go, well, I got a half a tank. No big deal. I got a quarter of a tank. Okay. No big deal. I got 1/8 of a tank. I better start looking for a gas station here soon. And oops, I'm almost on E. We need to do something. That's what the garbage collection does. The garbage collection says, at the beginning, it said, I don't care. But after a while, it's going to say, boy, we need to do something about this. So it'll pause your application, clean up memory, and then return your application back. Okay. So heap maintenance is done by garbage collection. It checks to see if there's any unused objects and it deletes them. How does it know if it's unused? Because a variable has gone out of scope. The first name gets created on line 26 and gets released on line 29. Now, it doesn't release it every single effort. As soon as that thing goes out of scope, that memory gets destroyed. No, it's kind of lazy. It kind of takes its time. So as it goes along, it's going to finally come out and say, hey, hang on a second. There's an awful lot of these things that we need to release. Okay. But the release is based upon what's called a, well, I hate to get too technical. It's called a link count. In other words, how many things are pointing to this spot of memory? When that count goes to 0, which means nobody is using this part of memory anymore, well, then it's eligible for being recycled, so to speak. Okay. All right, so one more time. The stack is kind of automatic. It kind of grows and shrinks as the program progresses. Typically, you don't do anything to manage the stack at all. The heap is where big things get stored. I want to create an array with 10,000 items in it. That's not going to be on the stack. Now, the variable that gets stored will be on the stack, but the 10,000 integers, no, those are not going to be on the stack. That's going to be on the heap. And if you create a bunch of those things, the machine's going to get lots of holes in memory, and garbage collection is going to automatically be called every once in a while. Okay? And it's all about scope. Let me go ahead and do one here. I'm going to go ahead and make me a pretty good size array. So I'm going to do an array of, I don't know, junk is equal to a new integer with, let's do 10,000. Okay, so 10,000 integers, that would be 40,000 bytes. Okay, so 40,000 bytes got thrown onto the heap. And then when we got to line 31, poof, they're no longer being used and they're eligible for recycling. Okay, I think you guys got this. Whew. Okay, on 291, they kind of go over it again. So let me just hit the highlights. You, the programmer, don't actually delete anything. You don't ever go say, oh, by the way, you know that array called junk, I don't need that anymore. You don't do that. It's automatic when things fall out of scope and the link count goes to 0. The machine knows it and does it all by itself. Local variables are on the stack. Okay? Actually, all variables are on the stack, not just local variables. But if they're primitives, that's the end of the story. If they're reference types, the thing that they point to is on the heap. Whew. So class instances, which are reference types, are on the heap, but their referenced variable is still on the stack. Okay. And you don't normally call the garbage collection. I have seen people do this before. For example, let's say there was a very timing critical thing. The only time I would ever invoke the garbage collection is if I was trying to determine like how fast like a sort routine was or something. You know, where a stopwatch kind of a thing where I want to make sure that I'm measuring the performance of this one piece of code, right? Well, I might want to run garbage collection immediately before because I don't want it to be automatically invoked while I'm doing my high performance test run. So only in very strange scenarios, like I've got a stopwatch and I'm trying to figure out which of the 3 sort routines is the best sort routine, you know, I want to not have my application pause in the middle and go do garbage collection because that'll mess up my statistics. But that's about it. So normally you don't ever call garbage collection and say, it's time for you to go scavenge and coalesce holes in memory. Okay, we're coming up on the 15-minute mark.